Alright, this is a question we left off on. A group of students must be separated into 3 smaller groups. So we have a class and we're doing class projects and you guys have to do presentation. And some presentations are more work than others, so I'm putting 8 in group A, only 5 in group B, they've got the easier project, and 7 in group C. How many ways could I do this? Well, there's 3 decisions I have to make. I have to decide who is going to be in group A, who is going to be in group B, and who is going to be in group C. In your group, does the order matter? No, you're still the same group whether I picked you in a different order. So this is a combinations question. And does it make sense there's 20 people, I could choose any 8 of them to be in group A. But then when I get to B, B is not 20, choose 5. Why? 8 people are already in group A. So now there are 12 people left. I need to choose 5 of them to be in group B. Now if you were in this class, and I just chose group A, and I chose group B, and you're still sitting there going, I wonder what group I'm going to be in. You're like, you're going to be in group C if you're left. I mean, we can do this, but do you see that everybody who's left, there's only going to be 1, but if there's 7 people left, we have to choose all 7 of them. Anytime you choose everything, the answer is going to be 1. 7 choose 7, which is 1. Now, the question is, what happens if on the day of choosing the groups, I decide I want to choose group B first, and then group C, and leave group A to the end? Should that change the answer? But look at the numbers. Instead of 20, choose 8, what do I start with now? It's going to be 20, choose 5. That seems different. And C, there's now 15 people left, and I need to choose 7. The only thing that would be the same is the people at the very end. I hope they know they're in group 8, because there's 8 people left. I have to choose all 8 of them. But those numbers are different. Does it come up to the same answer? Well, if we play around with the formulas. Okay, 20, choose 8. Remember what other number would be on the bottom here? 12. Remember that in a combination, the bottom 2 numbers add up to the top. And then 12, choose 5 would be 12 factorial over 5 factorial and 7 factorial. And 7, choose 7 would be 7 factorial. I mean, I should just write 1, but it's kind of neat to see the 0 factorial show up again. I'm just going to put a line through this because it's equal to 1. And the other one started with 20, choose 5, so it has a 5 factorial and a 15 factorial. Then we have a 15 factorial, and we would have a 7 factorial and an 8 factorial. And then this time I'm just going to write 1 for that last one instead of writing out the formula. Are they the same?
Just a question. Why is it generally like 0 if there's like in the last group you could put potentially different students?
When the last group, there's 7 people left, and there's going to be 7. They have to be in the.
Okay, yeah.
There's only one way of doing it.
Yeah, I see it. Yeah.
So that's why it's 1. If we use the formula for it, we get the 0 factorial, but that reminds us that by definition, 0 factorial is equal to 1. Now, do you see that in this first one, the only thing that would simplify is the 12 factorials would go away, and in the second one, the 15 factorials would go away, and both of them actually simplify to the same thing. Now, I like this as the best way to solve this question. I think the decisions of choosing group A, group B, group C, and using combinations makes the most sense. But when you look at this answer, doesn't it look like a Mississippi question kind of answer? Identical objects? And in fact, if you rethink this problem of like, I took all of you and I arranged you from shortest to tallest. And then I took the word I took those letters, and every word that I made, if I placed that on you standing from shortest to tallest, would make a unique group. And so it's another strategy that you could use the Mississippi question to solve this. Although I think our brain likes this better, because the Mississippi, you'd have to like arrange the students in a set order and then spell out all these words. But it's the same idea of I could cut these letters into a hat, and you're arranged in your order, and you pick one out of the hat as I go, and whatever word that's spelled makes your group. So it's kind of, permutations is kind of weird that way, because if you think of it with a different lens, it still might be a proper strategy to solve for. Okay. We had solved poker hands yesterday, right? All the poker hands was 52, choose 5. So now the question is, where did my deck of cards go? Oh no. Won't be able to solve this question without a deck of cards. I'll find it. We might have to resort to a new deck of cards. Worst case. They've got to be here somewhere, you would think. All right, we'll use the new one. We don't know if it can do the math as good as the old deck. That one was well trained. Okay, what if we wanted a poker hand with no clubs? All right, so I'll take, there's 5 cards. Did I win? Did I get no clubs? Oh, I got a good hand. But I got a couple of clubs. I didn't want any clubs. What would be the best way to guarantee that I pick 5 cards at random that I don't get any clubs? Well, I just go through the deck, and I'll show you a magic trick where I pick 5 cards and I get no clubs. Just have to set things up a little bit here by taking out all of the clubs. It's a good strategy, right? Be prepared to be amazed. Take out all the clubs. And now, miraculously, I picked 5 cards. Did I get any clubs? Amazing! If I did again, I could do this all day. But does it make sense that if you take out the clubs, and from the 39 cards, make every single group of 5 possible, you would get all of the hands with no clubs. It is a beautiful number. Check this out. That's a nice one. Nice. That's so cool. They're 57, 57, 57. I don't think that's the way you say that number correctly, but it sounds more fun. Poker hands without any clubs. And now, the moment you've all been waiting for. I may lie to you. Because sometimes when you do these questions, you think you're doing it right. So I'm going to introduce to you, I'm going to become a salesperson, and I'm going to sell you 3 correct solutions to this problem. And you have to decide if I lied to you every single time. Maybe all 3 are wrong. Maybe I just planted in your brain that I might be lying, and they're all 3 right. Or maybe 1 is right, or maybe 2 is right. You have to decide. So we are going to find the number of poker hands with at least 1 club. This is the correct solution, number 1.
This is question. Club. Can you just show me club for transitional what the word means? Okay.
What do you say in German?
I think
Oh my
it's
goodness.
like king, queen, and then like.
This is a king, but with this one right here, this thing.
Yeah, it's the suit, not the rank.
Oh.
What is it called?
Kleeblatt.
Hmm?
Kleeblatt.
Oh, so it's on the tip of my tongue.
Kleeblatt.
Okay, perfect. We'll stay with clubs. So I'm going to sell you 3 correct solutions, and you are going to obviously agree that all 3 are correct. Solution number 1, since I've already nicely got the clubs separated, and I want to have at least one club, I'm going to take these 13 cards and choose one of them, guaranteeing that I have, guaranteeing that I have one club. I then go back and take my cards and I put them back in the deck and I can shuffle it up. And now I have 51 cards left in this deck. And if I choose 4 more, could I get more clubs? Yes. Could I get no more clubs? Possible. I didn't get any more clubs. I didn't shuffle very good. But I take those 51 cards that are left and I choose 4 more. And I've guaranteed that I have 1 club, but I've made a set of 5 cards. I could have more clubs, so I have found the number of poker hands with at least 1 club. Correct solution, we'll call that one number 1. Correct solution number 2. We're going to use the knot strategy. The knot strategy says take all of them, well, all the poker hands possible are 52, choose 5, and then you subtract the bad ones. Well, which would be the bad poker hands? The ones with no clubs, which we just counted in part A. So if I just go and subtract 39, choose 5 from all of them, if I take out all the ones that have no clubs, I would be left with all the ones that have at least 1 club. Also good strategy. And correct strategy number 3, we could also do this with cases. It's going to take us a little bit longer, but in the cases strategy, we count exactly 1 club to start off with. So I have my 13 clubs, I choose 1 of them, and then I take my 39 other cards that are left, and I choose 4. That would guarantee that I have exactly 1 club. Case 2, exactly 2 clubs. Well, I take my 13 cards that are clubs, I choose 2 of them, and then from the 39 cards that aren't clubs, I choose 3 of them, and I'm guaranteed to have exactly 2 clubs. Can you see that we're going to have 5 cases? Case 3, 3 clubs. 13 clubs, choose 3 of them. Of the other 39 cards, choose 2 more. Case 4, 4 clubs. 13 clubs, choose 4 of them, and from the 39 cards, choose 1. And finally, case 5, all 5 of them are clubs. Take my 13 clubs, choose all 5 from there, and if I add up my cases, then I would have counted every hand that has at least 1 club, because I counted 1 club separately, 2 clubs separately, 3 clubs, 4 clubs, 5 clubs. And there are 3 correct solutions from this salesperson who's telling you that these are all right. But now you have to decide, did I lie on every single one of them? Or was I actually telling the truth and just making you think I lied? They all seem good, don't they? I think I did. I should quit teaching and try to sell. What are things that they?
I've noticed and I've done all the calculations on a calculator here, and I've noticed one of them seems.
Okay, let's put the calculations down. I like that idea. If all 3 numbers were the same, the nice thing about that is you would know I was either completely lying or completely telling the truth. But I couldn't be partially lying anymore. So the numbers are, for the black one,
32, 48, 700.
Okay. The green one.
20, 23, 203.
And the blue one.
20, 23, 203.
Ooh. Ooh. They can't all be right. I did lie. I'm so sorry.
Now, did you lie about all of them?
I could have still lied about all of them, then I'd have to be really, really sorry. Or,
You only lied about one. You lied about two.
did I lie about two and is one right? Now, there's something that we did yesterday that should tell you whether, like, it should confirm something for you. There's something we did yesterday where you can say, I know that either 2 and 3 are definitely wrong, or I know that either one is definitely wrong. There's something we learned that you can definitively tell me something is wrong.
Well, I can't quite definitively tell you something is wrong, but I can look at a past question and see for a similar type of question,
Mm-hmm.
we used the same kind of strategy. We used a very similar strategy that we did for number 1 on example 3,
Okay.
where we had a group of boys, a group of girls. We had them separate, like our group of clubs and non-clubs, and then we designated how many. But this is slightly different because we needed exactly 2 boys and exactly 3 girls. Oh, actually, yeah. That one we have clubs and everything, and then everything else.
Okay.
So a club and then everything else.
So does that definitively tell you something's wrong with something? There's something that we did that you can say right away, I know this is a pen, not a pen. I know this is wrong. What do you see?
For number 1,
Mm-hmm.
we kind of calculated grabbing a club, sorry.
Yeah.
A club from another deck and then just grabbing another 4 cards from the deck we actually have, but not having a 100% chance at least having one. So we did the calculations for the wrong case.
This is the 13 cards and the 51. They're all from the same deck. I have my clubs separated. I chose one, and then the leftover 12 cards I stuffed back into the regular deck, leaving 51 cards left. Chose 4 more.
I found it in example 2. We find a number of possible hands that you can pull from a deck, and it is lower than the answered one.
This 52 choose 5 is, oh my goodness. Something, am I close?
Yep.
How close am I?
960.
Oh.
You were
100 off.
Yeah.
There we go. Okay. There are about 2.6 million poker hands, of which 3.2 of them have at least 1 club. Does that feel wrong? It's like the shirts that say 4 out of 3 people have trouble with fractions. It's too much.
I think I see the fallacy in number 1.
Okay.
So it counts some hands twice.
Well,
So
obviously we counted too much because we got more than even possible.
yeah.
So give me an example of counting a hand. 13 choose 1, what could I pick?
2 of clubs.
I could pick the 2 of clubs. And then in my other ones, what could I pick for my 4 other cards?
3 of clubs.
3 of clubs.
And let's just go 3 of hearts, 3 of diamonds.
Ooh.
etc.
I need one more. You can't just say etc. I want to be specific.
3 of spades.
3 of spades. Wow, we got an amazing hand. Okay. So this is an example of what we could pick. What could be another thing I could pick when I do the 13 choose 1?
3 of clubs.
I could pick the 3 of clubs. Then I could pick
2 of clubs.
the 2 of clubs,
3 of hearts.
the 3 of hearts,
3
the
of spades.
3 of diamonds, and the 3 of spades again. In this counting method, those would be considered different Because in my 13 choose one, I could have chosen the 2, and then in 51, I could choose these. In the 13 choose one, I could have started with the 3 of clubs, and then put the other ones in it and picked these 4. But those are the same poker hand. So we overcount. How much did we overcount by? Oh, about 1.2 million. You know what? That was close. No, you're not even, that's not close at all.
1.2.
Because the real answer is 2, oh yeah, sorry, these ones are right. I didn't lie on all of them. These 2 methods are right. The answer is 2 million, just over 2 million. And when we got 3.2 million, yeah, we were out by 1.2 million, kind of a big deal. But it's because you overcounted. So what's the problem? What's the thing to avoid? When you're doing something where order doesn't matter, and you're doing decisions, you can't overlap. You can't choose something in decision 1 that you can then also choose in decision 2, because then you'll create a little bit of order, just like we saw here. We created a little bit of order when we shouldn't have. That's why, in the cases question, notice I'm choosing clubs and not clubs. Or before we did boys and girls, right here with clubs and not clubs, there's no overlap. And so it doesn't create any order. We can still say there's no order even though we counted it separately. But as soon as you have an overlap of something you can count in 2 different places, you can overcount quite easily, quite quickly. Okay. All right. And now that is the last one in your notes, right?
Yep.
In your textbook, you have I believe, an empty page on page 734. And we are going to learn the mathematics of poker. Why is it that one hand in poker is better than the other? Well, we're pretty good at common sense. Something's better if it's harder to get than something else. But why is it harder to get? How much harder is it to get? We're going to look at those things. And in order to do that, we're going to set up first sort of the strategies for counting poker hands. So here's our strategy, and the strategy is going to make more sense once we do some examples. It's a little bit, sometimes the wording in strategies is a little bit tricky, okay? We're going to every card has a number and a suit, okay? So, for example, in a poker hand, you could have a pair. You could have a pair of 2s, a pair of 7s, a pair of 8s. So what we're going to do is we're going to count the kind. And in cards, we call kinds the 2, the 3, the 4. They're kind of like the number, but we don't say number because then we're like, what number is queen?
Aren't those called the ranks, though?
Or they could be, that could be another word, but you don't say I have 3 of a rank in poker. You have 3 of a kind. So we're using sort of that language that poker says when you have 3 of a kind or 2 of a kind. The kind is 2 7s, 2 8s, the rank, the number, or the queen, jack, king, that sort of thing. And then I like to say specific card because if I'm choosing kings, there's 4 kings in the deck, which relates to the 4 suits. But you have 4 kings, choose 2 of them, and you have a pair of kings. Does it make sense that there would be 6 different pairs of kings? Possible, because 4 choose 2 is 6. The order doesn't matter. Doesn't make a different pair of kings if you switch the black ones this way or this way. But you'd have 6 ways of getting a pair. Okay? So that's the strategy we're going to use. We're going to count the kind first, then a specific card. And we have to count kinds of the same size, this is so that we don't overcount, at the same time. And you'll see what this means in our first and many of our examples. What does it mean if we have kinds of the same size that we have to count them at the same time? So we're going to start off with a pair. For example, a pair would be two kings, king of hearts and king of diamonds, and then three other cards that are all different. That is one example of a pair. So what we have here is we have, I'm going to underline these three single cards in blue and my pair in green. The three single cards are the same size because they're both all single cards, whereas the pair is a different size because it has two cards. So when I'm talking about kinds of the same size, I mean a pair takes two cards, but single cards take one. So what we have to do is we have to count the kind first. So let's say we're doing the green part first. I have 13 different kinds, and I choose one of them to be my pair. It could be the kings, that's what I had here, but it could be anything, right? You could have a pair of kings, pair of aces, pair of threes, pair of sevens. 13, choose one. And then I have to choose a specific card. So if I choose kings, how many kings are in a deck? 4. And if I want to make a pair of them, I have to choose 2 of those 4. So sometimes if you're watching YouTube videos, you'll see people saying, this is choosing, I'm choosing the number, then I'm choosing the suit. But I actually like to physically say, if I've chosen kings, I go to my deck, I take out the 4 kings. I feel it's like a better visual if I like pick which 2 of those am I taking. And I pick the red ones. So this together, if I underline this or I do this in green, this is all possible pairs. That counts every possible pair that you could get, because you said all 13 kinds could be possible, chosen. And then, if I took those 4 cards out of that kind, I chose which 2 all possible pairings of those cards are counted. Now, we have to choose our single cards. We have 3 single cards of the same size. There are 12 kinds left, because you obviously can't pick the kings again. And you need to choose all 3 of those at the same time. If you choose them at different times, you create order and you overcount. So that's why we choose kinds of the same size at the same time. Then for the 3s, there are 4 3s in the deck, we just need to choose one of them. There are 4 5s in the deck, choose one of them, and 4 7s in the deck, choose one of them. This will give me all the 3 single different cards that are possible.
So excited about the cards, we grabbed the calculator.
I was looking for the calculator now, because I pre-calculated this. We have a total of 1,098,240 pairs possible. So if you just took 5 cards at random, that's just under 50%. Right? 2.6 million chances, you have over 1 million chances of getting a pair. Right? What beats a pair? 2 pairs. This is where you have one pair of one kind, have another kind, and one extra card. If I color code, here's a pair, there's a single card. The pairs are the same size this time. So if I'm counting my pairs first, it could be any of the 13 kinds. I need to choose 2 of them. Because it's not like in your poker hand you say, oh, I have a pair of 3s and a pair of 8s, and the other person says, I beat you, I have a pair of 8s and a pair of 3s. My 8s are bigger than your 3s. You're like, that's the same thing. Okay? So we have to choose them at the same time. 13 choose 2. I chose 3s and 8s. This gives every possible 2 kinds that you have. Once you've chosen those, you see that you would have 4 3s in your deck. You need to choose which specific 2 cards you're going to have. And for your 8s, you have 4 8s in your deck, and you need to choose which specific 2 you would have. And this would give you all possible countings of 2 pairs. Next, we need a single card. How many kinds are left? There's 11 kinds left because you've used up 2 of them. And you need to choose 1. I chose kings, and then of the 4 kings, choose 1. This will be the all single cards. And in this case, can you see that you could have done 44 choose 1? There's 52 cards total. You take out the 4 3s, take out the 4 8s, because you can't get another 3 or another 8. Take out 8 cards, you'd be left with 44 cards left. Choosing 1 combines those together. I just kept it as the kind and the specific card, so we had the same format going through. Calculating this out, it is substantially better. 123,552. It's like 9 times better. Not quite. So when you get 2 pair in a poker hand, and that person, you're pretty sure they've given away that they had 2 aces and they're feeling really good about themselves, your hand is like 9 times better, even if you just have low pairs, but you have 2 of them.
Even if you have 2 2s, 2 3s,
Yeah.
still
You're like, ha ha. Okay?
And then 3 of a kind.
3 of a kind. This is the one where I really find the mathematics interesting, because, like, who decided 3 of a kind was better than 2 pairs? Well, math decided. Did they just play, did the first poker players who made the rules know permutations and combinations and figure it out? Or did they play it long enough and just say, it really seems that people are getting 2 pairs more often than they're getting 3 of a kind, so just based on experience, they made the order? I think they probably did the mathematics. Or whoever invented the game, somebody was like, you know, your mathematics are wrong. You should switch it. So let's look at this. 3 of a kind would look like this. So I would have, that's really exciting. 3 aces. Actually, 3 aces isn't that exciting, because probably someone is scared of the ace and they don't bet. It's more exciting when you have like 3 4s and they don't expect you to come through and win. But anyways, we'll have 3 aces. And then 2 other cards, which might be like the 7 of clubs and the 5 of clubs. So in this one, this is color coding, 1 size, and these are 2 single cards of the same size. So I go 13, choose 1. Happen to choose aces. There are 4 aces in the deck. Which specific 3 do I choose? This will make all of the possible 3 of a kinds that could exist. Then I need 2 single cards. They're the same size. I have to choose the kinds at the same time. 12 kinds left. Choose 2 of them. And then I chose sevens, 4 sevens, choose one. I chose fives, 4 fives, choose one. This will give me two single cards. And you know how we did the A, B, C grouping question? I showed you could do B first and then A, then C. If you decided to count the single cards first and did 13 choose 2, 4 choose 1, 4 choose 1, and then 11 choose 1 after, you'll get the exact same number. As long as there's no overlap in any of these, which there isn't, you're not going to overcount, and the order wouldn't matter how you did it because order doesn't matter to begin. This 3 of a kind is calculated on this calculator. There we go. About just over twice as good as the 2 pairs. So getting that 3 of a kind, you know you've done a lot better. Does anybody want to do the contest during class today? Okay, so if you didn't do it today, come tomorrow at lunch to start the contest. And yeah, it only takes half an hour. Feel like it's, what did you think? A little bit, some of the questions a little bit easier?
First one is always easy.
So then you get more chances to win free lunch at cafeteria in the draw, so it's good. Any hands you would be interested in counting? This is a technique that works really good. You could do full house easy with this technique. 5 of a kind is really hard to calculate.
Let's do Royal Flush. It'll be so hard to calculate.
Royal Flush is easy. Because there's only 4 of them. There's 1 in hearts, 1 in spades, 1 in clubs. Can't remember the 4th one. So there's only 4 total Royal Flushes.
Now, what would be interesting is trying to determine how much, like, straight flushes there.
Straight flushes aren't too bad, okay? Because first of all, in hearts, the straight flushes could go 8 through 5. That's 1. 2 through 6. 3, 4, 5, 6, 7, 8, 9. We're taking out the royal flush because that's 10. There's 10 straight flushes, but the last one is the royal flush, going from 10 to 8s. So there's going to be 9 straight flushes that aren't the royal flush. Per suit, times 4, 36 in total. And that's why straight flushes are second best behind royal flushes. 4 of a kind would be really easy because you just do 13 choose 1, 4 choose 4, and then 12 choose 1, 4 choose 1, or 48 choose 1. There's 4 of a kind is also super rare, but not as rare as the straights. Flushes is a little bit interesting.
There's a bit over 100 4 of a kinds. There's 104.
104. What's that?
104 days of summer vacation.
There is, like, flushes aren't hard to count, okay? Because for a flush, you have cases. Case 1, we'll start by counting the hearts. You're going to find out the cases are all identical. But if I took all 13 cards and chose 5 of them, that would be all the flushes. Then you'd have to subtract out 10, because those are the straight flushes. And if you had that, that would be even better. So we have to take out 10. And then whatever this answer is, multiply it by 4.
1277.
1277 times by 4 is 1277 the total.
Times by 4. So the total is 5108.
And check, like 5108 is just a little bit worse than a full house. So that's why a full house beats a flush, just barely. And if you've ever played, I don't know if you've ever played, for example, when you play, the most famous kind of poker is called Texas Hold'em, where you get 2 cards and everybody shares 5 cards. And you make your best 5 from your 2 plus the 5, so there's 7 cards out there. One of the reasons it's a lot of fun is because you're using 7 cards to make your best 5 cards, your chances of getting these better hands happen way more often, which makes it more exciting, but it also can make it really sad when you have that flush and somebody else has a full house. True story. I just happened to be playing poker on my phone last night, and I got the full house, and the other guy had the flush. And I took a lot, it's all fake money, but I took a lot of his fake money. I think I won like something like, reasonable, like $42 million. And
How many high cards are there?
And then he got really mad and just left the game. You get really, he thought for sure he had the flush. He was going to win. Everything was going to be good. He was going to go to bed happy. And I ruined his evening.
Now I'm curious how many high cards there are.
High cards. I don't know. If you consider an ace high, what about a king?
I just mean how many hands just have
Oh.
only the highest
Wow.
that's a high card. Yeah.
It's like all. Okay, that's actually a little bit. Okay, if you want all 5 different, it's a little bit tricky because the high card hand. First of all, it wouldn't be tricky if we didn't consider certain things. But there's 13 hands. You need to choose 5 of them, right? 13 choose 5, and then 4 choose 1, 4 choose 1, 4 choose 1, 4 choose 1, 4 choose 1. But from this, after you did this, you'd have to be like, oh, but I'd have to subtract flushes. What else would I have to subtract from here that could be good? 5 different cards that could still be better than. I'd also have to subtract straights that aren't necessarily flushes. And it gets a little complicated because straights, you could count, they get a little bit tricky to count because of their, you could have straight flushes or you could have straights with different numbers. You just need, once you've chosen to starting with an ace, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 1 for the ace, then 4 choose 1 for the 2, then 4 choose 1 for the 3, and counting that times by all the cases of all the different straights that could happen. But just all 5 different isn't hard to count. But high card makes it a little bit different because you'd have to take out these specific 5 cards different that are really good. But again, you can find all of that counting online. But I feel like this strategy of counting kinds first, then same size, same time, really counts a lot of them, and you can see where the mathematics of why something is better than something else. Okay? If we took our 5 cards, if we take that flush one, right? Got about a 1 in 509 chances of getting a flush. Should I deal out 5 cards randomly 509 times, see if we ever get one?
Yes.
Yes, no, you guys would probably like to work on other things. Stuff. Let's do it.
How do you deal out 5 cards to each of us?
It's gonna fail right away. at least red, but I didn't even get 2 cards in a row of this thing. Gotta try again. Over and over again.